at the some homework. So we can do the homework. Does somebody have? I don't want to touch it because I don't want to get your paper thing. So there was that. The one question was basically you had a slide, and then you came out like this. And this is what this was. This was 1 meter.
Yeah.
Yeah.
And then this was 4 meters.
Yes.
And then you had a kid here, and then there was a coefficient of kinetic friction of 2.6. That's what sticks in my head.
Yeah, and then there's the 37 degree.
And then this is a 37 degree angle. Okay. And the question is, you want that kid to come down here, then slide down here, and at some point stop right here.
Yeah, want to know like the distance.
And the question is, find D. Okay. So I told you how to start this one. How are you going to start this? First of all, you see the before picture and you see the after picture. So you're thinking conservation law. So why can't you say this energy equals this energy?
Because there's friction.
Yeah, this energy is going to be actually greater than this energy. Why? Because you lose part of your energy to work. So what are you going to start with? You're going to start with this fellow here. And all this says here is that if your energy changes, it's because you either gained it from non-conservative work or you lost it because of non-conservative work. That's all that equation states. So in this case here, what is the non-conservative work? The work done by friction. So you have the work done by friction here equals change in A. And what makes up the work done by friction?
Negative FFKD.
Okay, so the friction on this part and then the friction on this part. Okay. So you're going to have two parts here. You're going to have the this part of the friction, okay, and then this part of the friction. So let's actually write this down. So what would be this part of the friction here?
The normal times the normal times u sub k times the distance.
Yeah. So if you have your, well, here's your normal, and here's your mg, and here's your kinetic friction. Okay. What are you going to have? You're going to have this kinetic friction here, which is going to be your mu sub k times the normal. The normal is going to be what? In this case? It's going to be this y component of the weight, which is
Sine or no cosine.
mg cosine of theta. So this right here is your kinetic friction on this part here. Okay. And what do we have to multiply that by? That's just, we need the work. The distance, and it's this distance here. This distance right here is 3. I think this turns into what, a 3, 4, 5 right triangle? So this is what, probably 5?
Yeah.
Yeah.
Okay. So this length here is 5. So you'd have 5. Okay. And then is this positive work or negative work?
Negative.
Negative work. Okay. Good. What would you have then for the section over here? Hey, Peter.
The same as another.
Yeah, so now you have minus, you need your kinetic friction. So it's mu sub k times the normal, what's the normal over here?
It's just mg.
Mg. And then times this distance here, dw. And this has to equal the change in energy. What is energy always made up of?
Kinetic and potential.
Yeah, so this is going to be this E final minus E initial. It's going to be your KE final, U final, minus KE initial, U initial. What's your final kinetic energy here?
0.
Because the kid stops. Plus, what is your final potential energy?
It's just well mg, but it's or mgh, but it's just mg because it's a meter above. H is 1.
You could do that or you could do 0. Either one's fine. How come? I'm going to get two values here.
We cancel out.
Because it doesn't matter where you take the origin.
It doesn't matter. So you have different heights here. Where do you want to take the height? Do you want to take this to be the height, or do you want this to be the height? You get the same answer either way, just as long as you're consistent. Pick one.
Sandy's trying to join the call.
Who is?
Sandy. And it's saying that you haven't started the meeting.
Is she on the lab link?
I don't know.
She needs to be on the lecture link.
Dr. Lynn.
Yep.
Can you look at that? 'Cause I did.
Let me finish this first,
Okay.
and then, okay. So, the U final here, so do you want to take this to be the ground, or this to be the ground? I don't care.
Take the bottom one we heard.
We'll take the bottom to be ground. So this would be M, G, I'll put the 1 here like that, like this. Minus, now what about the initial kinetic energy?
0.
Because
Kid starts at rest.
kid starts at rest. Plus, what's your initial potential energy?
And
Again, I'm using this now as the ground.
4 mg.
Yeah, so then we need the H here is always the vertical distance above the ground. Did that help her at all? Aaron? Or don't you know?
She said I'm using the one on campus. Didn't really specify.
There's an actual link that I sent out for myself some earlier. Can one of you people there and who are doing this, could you send the link to the class to Sandra?
It's not on campus.
Yeah, I can.
Okay, thank you. So this will be then MG and this will be 4. Okay. And then what variable are you going to solve for?
Yeah, solve for D.
You're going to solve in this for D. Now, why did they give you the mass of the kid?
Because the math cancels.
Yeah, all the masses. Usually, if they don't give you a mass, or it could be a mistake, it probably means that it's going to cancel. So they all go off. Okay, that's what that one. Does that make sense?
Yeah.
Any other questions on this guy?
I guess it's not, it's just, I did it a different way. I don't know if it works out. So I broke it into like 2 pieces.
Mhm.
And then I did like that stuff just for the first.
So you did this part here, and then you did this part here?
Yeah.
It's the same, it ends up being the same.
Okay.
A little bit longer, but it's not one bit wrong. Pretty much fine. Yeah. Make sense? Yes, sir. Others on this? Okay, let's look at the next problem. Steve, why does that make sense?
Yeah, I was just a little bit confused. Why the KEF was 0?
Because you want the kid to stop at the end. So you want you want the kid to slide down and they stop here.
Okay.
That makes sense. Does that make sense?
Yes.
Okay. So now let's look at the next one. Okay, so this is working from memory. Is that right?
Yeah, that's fine.
And then there's friction here like this. And there's a spring here like this. You have it like that. And this is some R. And then what do they want for part A of this? And then they tell you up here that the velocity is something, right? They tell you that the velocity here is 12. And then there has to be some height here. What is the height? 2. Well, what about the height here?
They gave you the radius is 4, so the height is 8.
Okay, so this right here, this height here is going to be 2r. So this would be 8. Okay. And so for part A, they told you to find
That's friction.
the work done by friction or the use of K or the.
Use of K is.
Okay. So for part A, find use of K. And I think they also put the K here. K is what?
3,000.
30,000. And probably the elongation, and then the compression is
-2.
2. So in other words, it's compressed that way. If you want to call that -2, that's perfectly fine. That's work. Okay, so you want to find use of K. So they give you this point, and you know this point. What does it smell like?
Non-conservative work.
Yeah, it would be, you could say that this energy equals this energy if it wasn't for what?
The friction spot.
This stupid spot here. And I think they'd give you the width of this stupid spot. How long?
2.5 meters.
2.5 meters. So you can't say this energy equals this energy, so you have to back up one step. And you have to think, okay, why is this energy less than this energy? Because you've lost work to friction. So you have your non-conservative work equals change in heat. And this equation is always true. Okay? This is an always true equation. You tell me how to do it.
Well, you start with like use of K on this side.
Okay. So the work, non-conservative work is going to be the work done by friction. So this would be the work done by friction. And what would be the work done by friction? Okay, which is just going to be your mg times the distance, your d. We'll call this d. Okay. So this right here is your friction force. You take your friction force times d, it's negative, so that's going to be the work done here. That has to equal your E final minus the initial. Okay. So what do you have? Minus mu sub k mgd equals, what's your final energy?
Kinetic final plus potential final.
Kinetic final plus, and we're going to use this point here. This is going to be your final point, okay? Because we have the velocity at that point. Okay? So what we have, we'll have the 1/2 the mass times v squared, and this v here is going to be this guy, right? Plus what? This mg2r. This guy is here. So this whole term here is my E final. And subtract from that my E initial. What's my E initial?
Well,
Oh, actually, yell at me here.
Yeah, there should be.
Plus 2. What do I have to add 2 there?
so 2 feet above, or 2 meters above.
Yeah, there's an additional 2 things here. So this whole height here is the same plus 2. Okay. Keep going. Now, what is my initial energy?
Your initial is kinetic initial is 0 because it's at rest.
Is that rest plus?
Plus 1/2 kx squared.
Now you have a string, 1/2 kx squared. And you go through this and you crank this out, and you get mu sub k equals something. Does that make sense? Okay. What is part B?
I have a normal force. I
Okay.
have not really.
I think I told you before that my cats write all the exams. The day before I give the test, I take out my computer. I tell my cats what should be on the test. And in the morning when I go and feed them, they hand me back the test. There's usually some mice I have to take, some mice questions I have to take out. But for the most part, that's the test. It turns out my cats really like questions like this. They're big fans of these questions. Okay. Who can understand a feline brain? That's why Batman can never defeat Catwoman. Crazy. If it was like Giraffe Woman, she'd be in Harlem, okay, with all the other villains in Gotham. But it's because she's Catwoman and you can't understand a feline brain. Crazy. We're learning a lot. Some of it's true. Okay, so the next word is find the normal force here. How do you find the normal force though?
Draw a free body diagram.
Yes. What are the forces on it?
Normal and weight.
Okay. Now what? Which is what? Why are you saying radial perpendicular? How do you know it's a circular motion problem? It's going in a circle. Okay, so it's a circular motion problem. Toward the center of the circle is positive. So you have your normal plus your weight equals your m and your radial acceleration, which is your v squared over r. So your normal force is going to be your mv squared over r, and then your weight is mg, so it's minus mg. So you have your v, you have your r, you have this fellow's Shazam. That make sense? What's the last part?
It asks about finding like the height at the end of it when it jumps off the track.
Okay, so so the problem here, you have this, goes like this, goes like this, goes like this. So it comes along here, loops, comes up here, overshoots and goes up here. And did they want that maximum height from here, or where did they want it from?
I think they wanted,
Probably this guy here.
yeah,
That we're down to the bottom?
I don't remember.
I think it's down to the bottom.
Bottom, down to the bottom. Okay. You tell me what to do. What do you know about, and then here's a little friction. What do you know about this whole part here?
There's no friction, so instead of making it harder on yourself, starting from the beginning, just start from the loop, because then you don't have to worry about friction.
Yeah, what do you know about energy along this whole region here?
It's the same.
Has to be the same, because there's no friction. So I can say E initial, so this part here is frictionless. So I could say E initial equals E final. These cancel, so I equals F. So near at the letter F, this is really I squared. I is the square root of -1, that comes in squared, so it's equal to -1. Okay. Is that fine? Just a little Friday humor. Okay, sorry. Friday humor. Okay. Watch me just connect my thumb. Oh, crazy. Okay, so E initial equals E final. Okay, so what's your initial energy?
Kinetic plus potential.
Yeah, we're going to use this point here. Why? Because we have everything for it. Okay, that's the only reason why. So we have our 1/2 or m v squared plus mg. I'll call down here to the bottom again. So this would become our 2r plus our 2, just like before. That has equal. Well, what's the energy here? If this is your maximum height.
It's just the potential.
Yeah, this is just all potential here. This is mgh max. That makes sense? Questions? Okay, let's add to the initial. And we're going to start linear momentum today. Then we're going to couple it to our energy stuff, and we're going to get actually pretty specific things. Okay, so we're going to talk about linear momentum. Okay, and then pulse. So we have our little object here. Let's say here's an object. And let's say here's some force here. I gotta say a little bit more than that. Oh, we leave it like this. So we say our net force. What does the net force equal? MA. So this is always true. Now let's look at the average case. So suppose we know the average force. So I'm going to say something like our net average. So take the average of both sides here. Will equal m times a average. Well, what's the definition of average acceleration? This is by definition. Perfect. Right? This we know. Our average acceleration is your change in velocity over change in time. And put that in here. Okay, we're basically done. I'm going to take the delta t over here. Equals m delta v. How do we define a delta? Always the final minus initial. So this is mv final minus v initial. And let's multiply this stuff through. So we can get our f here. Delta t equals m v final minus m v initial. Okay, we're done. To be honest, this is it. We defined some things. We defined the linear momentum okay, as P equals mv. But this starts with the letter L, this starts with the letter M, therefore you use a symbol P. Little joke. Okay, but we do use P. P is always used for linear momentum. Okay? This side over here, this left side here, that left side here is by definition the impulse. This is the definition of the impulse. Okay, so what we have here is that the impulse equals P final minus P initial, right? Because if M times V is your linear momentum, then M times V final has to be your final linear momentum. And then M times V initial then has to be your initial linear momentum. Hey, what is the final minus initial column? A delta. So this is your delta P. So this right here is your net force, your average net force times delta T equals your change in linear momentum. Okay. This is a famous equation. Turns out it's used everywhere. Okay, I'm going to put a place for that. This is called the impulse momentum relation. Okay. So this is going to be, if you play any sport, pretty much anything you do. Okay, any sport is basically based on this. And it's used, we're going to use it next semester. We're going to do thermodynamics next semester. So we're going to do a lot with PV equals nRT and pressure and stuff like this. And that's going to come in for a lot of our stuff. You're going to see where we get PV equals nRT from. Now, a couple things here before we actually do some examples. I want to talk about the units for P. So what do we measure linear momentum in? M is measured in kilograms. V is measured in meters per second. So these are the units. Okay. Kilogram meter per second, they're the units for linear momentum. Okay. So what I want to do is I want to show you how you use this with sports. So this is the basis. Basis for most sports. So let's see how that works. Okay, I lived in South Carolina for 2 years, and as far as I can tell, I was the only one person in the state that didn't play golf. Okay, I think it's kind of a joke. But so most of the people in the state like to play. Although, if you hang out with golfers, some of them actually belong to country clubs, and they're forced to pay these ridiculous fees to be in the country club, which means that they have to eat a certain number of meals at the country club. So if you end up hanging around with them at the end of the month, you usually get a free meal because they haven't used up all their allotment of food. And so they treat you to a free meal. So you can sometimes get free meals. Okay. So other than that, I think it's a really stupid thing, but that's just me. So let's look at how people play golf. So here's the golf ball like this, and here's your club. Okay. What's the initial momentum of the ball? 0, right? So this is at rest. So V initial equals 0. So that means that P initial equals 0. Well, what happens? Well, the club comes along and makes contact with the ball. So there's going to be some force. So this is going to be like the average net force that the ball, I would just say the average force that the club exerts on the ball, whatever that is. Okay. And what is that going to do? How long is this club in contact with the ball for? It's in contact with this time delta t. So the club is in contact with the ball some time delta t. So this delta t here, this is going to be your contact time. Okay. But what happens? What's the next thing? Well, you follow through with your stroke, and then your ball flies off this way. This is going to have some velocity v final, and so your final momentum is equal to m v final. So what happened here? The linear momentum of this ball changed. It was initially 0. Now it's off with some mv final here. Why? Because this bat here put basically an impulse on it. It put this impulse on it of. So you take the F from the, you take this guy here, your average club on the ball. This right here is the impulse that the club exerts on the ball. And what does this impulse do? It changes the momentum of your ball. Make sense? Let's have this look like a real sport now. Let's look at baseball. Okay, so here's the picture. As a bat, the ball is coming in like this. So the system velocity would be initial here like this. So your initial momentum would be mv initial. Just out of curiosity, is that a positive momentum or a negative momentum?
Wait, is that m's momentum, right? It's not mass.
This is the mass. P is momentum.
Okay.
Okay, negative is going to the left.
Yeah, this is a negative momentum here. Okay. When when I was in grad school, it turns out there's an official physicist for for baseball, believe it or not. When I was in grad school, he actually came to give a talk. It was one of the few talks where the entire room where I went to school was a large university. And so they had one of these rooms that would fit like 400 to 600 people. When he came to give a talk on the physics of baseball, that entire room was packed and there were people actually in the aisles. Actually gave a fantastic talk. He was about 483 when he came. But he was the official physicist for the baseball team. He actually wrote a book called The Physics of Baseball, which is actually an excellent book. I digress. Okay. So what's going to happen? The baseball's coming in here like this, and then what happens?
Swings and goes yard.
Yes. You swing after your head gets disconnected from your body. That's unfortunate. Okay. One of the main hazards of playing baseball. The ball comes in contact with, the bat comes in contact with the ball. So this would be the force bat exerts on the ball. Average value here. How long is that going to be in contact with the bat for? Sometime delta t. So the bat is in contact with the ball for some time. Well, what's going to be the next part of this? Well, the next part of this is reattached. He follows through, the back goes through, and then the ball goes off like this. So this is some velocity v final, so your final momentum is mv final. So what happens here? You have this initial momentum going to the left. The bat comes in here, puts has a force on it for some time delta t, so this is your impulse. So your impulse is occurring here. So this is this average force of the bat on the ball. And what does that do? That changes the momentum to this. Okay? That makes sense?
So like, would you ever ask us to do like the momentum from the dude throwing the thing to the back?
Oh, all the time, and then finding the force if you know the contact time. Okay, now here's something that happens. Usually, at some point when you're a physicist and somebody finds you're in physics, they'll start asking you questions. And they'll say, well, what's the force of, and then they'll put in some value like this. Not realizing they're asking you a hard thing. So one thing if you're a physicist that you could ask is, so suppose you're walking down the street and you get hit by a car. What's the force that the car exerts on you if you're hit by a car? Okay, you're going to be able to understand how to do the calculation, although it's going to be actually quite hard. So let's do an application here. So let's ask, how would you find force that car exerts on someone if when you're hit by a car. Here's a car. This way. Here's a pedestrian. Hit. This. The question is, what is the force that the car exerts on the person? This is actually a hard question.
Depends on the speed, right?
Depends on a lot of things.
And distance.
Okay? Let's figure it out.
Is the person just standing there, or like, because I feel like, even though it's, person can't move that fast, but like, well, I don't know, like, some can't, but
Okay.
anyway.
So, okay, let's say this person is walking this way. So we're going to be initial here. Let's say after the accident here, this person has some velocity v1. Okay, it can be, you know, it could be, if you want it like this, you can have no. Okay. This is a really hard question to figure out. What would you go about doing this? You now know the physics behind it.
Just break them amongst components.
Yeah. What's your overall idea here?
Context.
You're going to have to know the contact time. This is nothing but the impulse force, the impulse momentum relation. So here's your initial momentum. MV initial. Okay. What's your final momentum? Well, it's over here. This is MV final. Okay. So let's say you had a camera here. If you had a camera here, you could actually then figure out what these are, because you know how long it would. You could actually measure things. If you had a recording here. Now, what would happen here? This is where the impulse is occurring. Okay, this is the impulse is right here. Again, so what's going to happen? That car, this will be the average force that this car exerts on the pedestrian. Uh-oh. Okay, pedestrian. Okay. And then how long is that force going to be on that pedestrian? Delta t. So this is the contact time. So what do you have? You have that the average force here car exerts on the pedestrian, times the contact time, the time that the pedestrian is in contact with the car, equals in the P final of the pedestrian minus P initial of the pedestrian. So your average force here is your change in P here, this guy, over your change in T. What do you think is really hard to determine? The contact time. So how long are you in contact with the windshield if you're hit by a car?
Really quickly.
Yeah, it's not like 2 seconds. I mean, what would be 2 seconds? 1/100, 2/100. You're not in contact that long. It's an accident occurs just like that. So this is something on there to like 1/10 of a second or a fraction of a 1/10 of a second. This is really, really tiny. The smaller you make this delta t, what do you know about the force?
Greater.
The greater force. Okay. And you kind of know, okay, do people still, when you're in showers, take a towel and twirl it around like this and let people with it? Do they still do that?
It's gonna die down.
Really?
No, yeah, not really. Or no, yeah.
Okay, well, if you're to do this, okay, so there's some things that are probably good that they die. That's one of them. It's like punching a rabbit in the nose. Hopefully that one dies.
I've never heard of
Well, that's a good one to die. You know, punching the rabbit in the nose is
Wait, a reverend or
a rabbit.
Never heard of that.
When you pull out your pockets like this, pull them in outside, and somebody punches you in the crotch.
Oh,
Yeah, that one is probably a good one to die out. Okay. This is, that's good. Swirlies?
Yeah, those died too.
They're good.
What's a swirly?
So you like dunk someone's head in the toilet.
What?
Yeah,
Well, that's
that's
how you-
good. Okay, so things are improving. Good. Okay. But when you did this, when you took a towel and went like this and throw it on like that, why did that really hurt like that?
Just stung for that, like.
Because your delta t is really, really tiny. Okay, your delta t when you do this is quite small, so you can get this ridiculous force coming out. But, you know, you're just like, oh, that really hurt. Okay? That's how that stuff works. Okay? So, but the point is that if you want to know how, you know, the force that the car exerts on the pedestrian here, what you have to do, you have to know the contact time, which is not one bit obvious what that would be unless you'd have like a videotape recording it. And then what else would you have to do? You have to know the V final here, and you have to know the V initial. You could probably see as small compared to this guy, so you could probably take this to be 0 and not be that much of an error. You also have to know the mass of the fellow too that guy had. Okay, so it's a really, really hard question to do, but at least conceptually you can see how you go and calculate it. So you also hear things like, what is the average force it takes to break a board? Okay, that's a ridiculously hard question. Why? So here's a board, you're going to chop up, and then you're going to break it with your hand. Or fuck, it doesn't matter. Okay. What's the hard part there? Okay, so the contact time, that'd be hard to measure unless you have a camera there. What's your mass?
The mass of their hand or the body?
Well, that's actually that, you know, because you're going like this, and it's, you know, it's going to be some mass here, but how much of your mass here? You know, that'd be a really, really hard thing to calculate. Okay? So those things you can ask sometimes, questions like that, but they turn out to be, and you can even know conceptually how to do it, but to actually go through the calculation is really, really hard. Okay? That makes sense? Now, let's do another thing. Let's do an actual example. Okay. Let's see, here's a ball. We have a ball like this. Let's say it's a one kilogram with the ball. So there's a velocity here. Let's say this is 30 degrees. Let's say this velocity here is 10 meters a second. Let's say that this is 10 meters a second this way. Let's say 30 degrees like that. And let's say I want you to ball is in contact with the floor for 0. Let's say 0.1 seconds. Okay. I want you to find the average force. The floor exerts on the ball. Okay, what do you do that? Do they still do what, release?
No, it turned into Twitter fingers, like social media crap.
We can do one-to-one mapping. We can find out what the what Willie went to. We can find out what we can do a mapping. And then we can publish a paper on it. And then get government funding. Okay, so how do we do this?
So wait, I'm assuming that the ball's like bouncing off the ground. Right?
Yeah, they
Like
can
it
go.
goes fast or something.
Right, ball comes here, boom, boom.
Have to do the average of the floor and the ball.
Okay, so we're going to have this is an impulse momentum relationship problem. What would be the indication this would be impulse momentum?
It's like saying how it's in contact with the floor.
Yeah, you say something with the contact time, you know it's going to be some sort of impulse momentum. Now, also, we're going to get a collision here. From now on, whenever you see a collision, when two things smash together, okay, you're going to start thinking somehow linear momentum is going to be tying in somewhere. So as soon as you get a collision here, you see something like a contact time, you're going to think linear momentum. Okay, so this will be the floor of the ball. Delta C equals the change in the momentum of the ball. This is what kind of equation?
Later.
Oh, vector equation. So what can you do with it? Break it into components. I'm going to stop the word average because I'm just tired of writing it. And the same thing then for the one. Keep going.
Is there any abbreviation for the whole? Like,
You can call it the impulse.
okay.
If you want. Usually, if you want the symbol for impulse, it's usually J. So J is really the symbol for the impulse. Okay, keep going.
You have to do then like the P final and P initial.
We have to do the P final minus P initial. So let's deal with let's look at the X1 first. Keep going. What is linear momentum always? Mass times velocity. Okay. So this is going to be the mass of the ball times the final x velocity of the ball, minus the mass of the ball times the initial x velocity of the ball. How do we find those?
You have to calculate the x component.
Yeah, we need to find Vx here and Vy here for this. Okay. So I'm going to draw this picture a little bit bigger over here. Vx, this is Vy, and this right here is our 10, and this is 30 degrees. So what is Vx? And these are the initial vectors. What is Vx initial and what is Vy initial?
This is the 8.6.
Okay, so this would be 10 cosine of 30 degrees, which is this 8.6. Talking about Vy. This would be 10 sine of 30 degrees equals 5. And tell me why that's almost true.
It has to be negative
How come?
because the velocity is going down.
Good. This is downward. Remember, it's a vector, so we have to worry about the direction. Okay. Now what do we do?
Same thing for the end.
Same thing. Or in the words of Scooby-Doo, ring ring. Ring ring, Maggie. We're learning so much here. Some of it's true. Okay. Vx final. This is Vy final. This is 30. Okay, what is our Vx final? Yep. So this will be our 10 cosine of 30 degrees, or 8.6. V final? Yep, this will be your 10 sine of 30 degrees, or 5. Is it positive 5 or negative 5?
Positive.
Because it's going upward. Okay, so what is our net force in the x direction?
0.
Yeah, there's been no change here. Notice this right here and this right here, these are the same. So what happens here is that this right here is going to give me 0. So that means that this force is actually 0. So the force in the x direction on the floor, on the ball, equals 0. And that makes sense because its momentum in that direction hasn't changed. Now what about the y? What do we have for that? So this would be mv final y minus mv initial y. So what do we have? And take this over on this side. Okay, what is mass?
1.
I think it's 1, right? This is 1. Our V final y is
1.
5 minus mass of 1. What's our V initial y?
Negative 5.
Minus 5. So notice these do not cancel because of this minus sign here. This is negative here. They're going to add. The contact time is what one? If we work this out here, this is going to be what? This is going to be 10 over 0.1 or 100 newtons. Is it positive or negative? It's a positive force Y.
Going up.
It's going up, and that makes sense because the initial Y momentum is initially going down. That impulse is going up, and that actually changes that momentum. So that's also going up. That makes sense? Okay. Next semester, we're going to study pressure. What is pressure? Most of you have had chemistry. Force per unit area. How does this get used in calculating so this is a room, it's full of the gas. How do we calculate the pressure from that? Why is there a pressure here in this room? What are the molecules doing?
Colliding.
They're colliding with us or with the wall. When they collide with us, what do? We put a force on the molecule, putting it outward like that. But by Newton's third law, what does the molecule do to us? Put an equal and opposite force on us. So we have all these molecules hitting us. Okay? They're all putting little forces on here. If you take an average of that force, that's going to be of those forces. That's going to be some force on you. Then over the area which is distributed, that's going to get pressure. So basically, we're going to do this calculation here for basically with so here's your wall. Let's say here's a molecule. The molecule is going to come along here, ricochet like that. The wall would put a force on the molecule, causing its momentum to change, but then there's going to be a force right here. This will be the force from the molecule on the wall. You can have a whole bunch of these collisions occurring. So you can have a whole bunch of forces, so there's going to be some sort of average force over some area here, and that's how you're going to actually calculate the pressure. Okay, it's going to have a very macroscopic origin. Okay, have a fantastic weekend.
Professor,
Yes, Silva?
I have a question. It's weird, like why sometimes you use like MGH to be like a UF, but sometimes you use 0.5 mx to be like UI.
Oh, it depends on what you have. So if you have a spring, you have to have 1/2 kx squared. Where k is your spring constant, and it actually tells that spring is compressed along with it. Whereas something that has a different height, you have to use MGH, because that's gravitational potential energy. So there's two types of potential energy: gravitational, and then spring potential energy. Does that make sense?
So when we have the spring, we have to make sure one like
You have a
one.
1/2 kx squared then.
Okay. Okay. Thank you.
You're welcome.
See you Monday.
Take care.